Okay, so in this session what we're going to address are the cardiovascular responses to exercise, and we're going to understand a little bit more about the background physiology in terms of these cardiovascular responses, but also start to consider the ways in which we can assess cardiovascular responses both at rest and during exercise, and also make some comments about the way in which we can interpret the data. So we're really trying to present an overall picture as to the nature of the cardiovascular responses both at rest and during exercise. Now, in order to do that, we have a series of aims that we need to think about. So first of all, we're going to look at the idea of generating an understanding of the interplay between exercise intensity and cardiovascular response. And this is a real fundamental starting point, because in order to be able to understand the way in which the cardiovascular system responds, we have to understand the way in which intensity plays a fundamental part in that. So the cardiovascular responses are very different if we compare, for example, moderate intensity exercise to either heavy or severe based exercise. And then if we go beyond the aerobic range, then we move into the more anaerobic exercise, and the cardiovascular responses become very, very disproportionate to the exercise intensity. Then we're going to try to think about the physiological rationale for the responses that occur. This is the kind of the why. So the first bullet point is the what happens. The second bullet point here is, well, why does this happen? Why do we, for example, see and observe that heart rate increases in response to exercise intensity? Why is it that we see, for example, an incremental increase in cardiac output in response to exercise intensity? So we're going to start to look at the mechanisms that sit behind these responses. And then finally, pretty much over bridging the whole of this topic area is, well, how do we assess these cardiovascular responses? How can you actually accurately record heart rate? How can you accurately record cardiac output or stroke volume or blood pressure? Because in the end, it's about the tools that we can use that are going to generate this reliable data that really generate our understanding of what is going on in terms of cardiovascular physiology. Well, in order to do this, we need to, first of all, think about the body in the shape of this schematic here. So this was originally proposed by Carl Wasserman back in the late 70s, and then reproduced in his textbook back in the 90s. This schematic here has been updated by Andy Jones, who's based down at Exeter, in a publication that was put together actually on oxygen uptake kinetics in MedSci Sport and Exercise. But it's actually a very, very useful schematic for us, because what it shows us is the sequence of events that are involved in the ability to move oxygen from the external to the internal. But sitting at the heart of this, and I excuse the pun there, is the cardiovascular system. So the whole key for aerobic exercise is we're trying to maintain a supply of oxygen consumption to oxygen demand. So if we follow the schematic through, from the left hand side we can see VO2. So VO2 is the volume of oxygen, so it's the oxygen uptake. So we have the process of inspiration. We extract the O2 from the ambient air. Via the process of inhalation, that oxygen is transported through the airways, it passes across the alveoli and through the lung. There it passes into the pulmonary circulation. Once in the pulmonary circulation, that movement of that oxygenated blood, which is now bound to hemoglobin, is generated through the pumping capacity of the heart. And the pumping capacity of the heart is really a function of just two components. That's the stroke volume, SV, which you can see in the middle, and the heart rate, which is HR. And in fact, if we multiply the stroke volume by the heart rate, you get what is the cardiac output. So the stroke volume is the volume of blood per beat of the heart. The heart rate is in essence the count of the beats. So the cardiac output is actually the volume of blood that's ejected from the heart over the course of 1 minute. So now we direct the blood through the circulation. You can see that it's then directed into the peripheral circulation, so we've gone from arteries to arterioles into the capillary network. At the far right, what you can see, where we have the mitochondria, are two very unusual components, which are QO2 and QCO2. QO2 refers to oxygen uptake at the muscle. QCO2 is of carbon dioxide production at the muscle. So under steady state conditions, VO2 should match QO2. And the production of carbon dioxide is a function of that steady state condition. So the O2 is delivered, the O2 is passed from the circulation, it's passed to the myoglobin, and then it allows for the process of oxidative phosphorylation of the muscle. The CO2 is then imparted from the mitochondria, it comes back through the peripheral circulation, again using the pumping capacity of the heart, and then we have the process of exhalation, and we then have the VCO2. So when we measure oxygen consumption at the mouth, using either breath-by-breath systems or Douglas-Back systems, and we're recording VO2 and VCO2, what you have to remember is that what we're trying to do by recording these at the mouth, we're trying to estimate what is going on at the muscle. But at the heart of this is this component, which is the cardiovascular system, the ability to move, direct and shunt both oxygenated and deoxygenated blood through the periphery to the locations that we require it. Now, when we think about this, we think about it as a two-component system. We think about oxygen delivery, and we think about the idea of oxygen extraction. So oxygen delivery is very much the idea of the pumping capacity of the heart. Now, given that heart rate times stroke volume gives us cardiac output, the primary unit of measure, or the primary unit to describe this, is cardiac output, which is abbreviated by the letter Q. Coupled with delivery, we have the concentration of O2 on the oxygenated side in the arteries, and that is CaO2. And this is a really important point here. Remember that during exercise, the one variable that is going to change, assuming we don't change anything environmentally, is the cardiac output, but the O2 concentration in the arteries will not change. The only reason that would change is, for example, if we change the either the barometric pressure, or we change the amount of oxygen that we could extract from the ambient air. So we reduced it. So we're assuming actually that cardiac output is the driving variable on the O2 delivery side. On the extraction side, it's very much about how much of that oxygen that's being delivered that's being extracted. So we're making the statement that the O2 concentration is constant. So on the extraction side, it is defined by what's called the arterial-venous oxygen difference, A for artery, V for venous, and O2 for oxygen, diff for difference. So the AVO2 difference represents the difference, that is the amount of oxygen that is extracted between the arterial side and the venous side. So the net result is what we have is Q times AVO2 diff, because the concentration of O2 remains constant. And we can define that as such. VO2 is what we measure at the mouth, is a function of Q times AVO2 diff. And that is referred to as the Fick equation. And it is a fundamental component of exercise science, that the amount of oxygen that we consume, which is a direct proportion to what is being demanded of the muscle, is a function of the amount of oxygenated blood, and therefore just oxygen that can be directed to the tissue, and the amount of that oxygen that is extracted at the tissue. So it's a really important point. So you can see why an understanding of cardiovascular physiology is fundamental to our understanding of exercise physiology and exercise science. However, we would be remiss if we didn't just take into account this. Now this is all tied into this whole component, particularly in relation to the extraction part of the equation. The delivery part is pretty constant. It's cardiac output. We know the concentration remains constant. But the ability to extract is a function of two key components, the DO2 and the PVO2. So the DO2 refers to the dissociation of oxygen, and this is our understanding of O2 dissociation curves. And the O2 dissociation in itself is a function of the partial pressure of oxygen, and the degree to which we have saturation of the red blood cell. So what we need to do is we need to have oxygen that is released from the blood cell into the muscle cell. So what we are looking for is we're looking to come down the dissociation curve in order to reduce the saturation of the blood cell. Not massive reductions. We don't want to have a reduction from say 98% down to 80%. That would be lethal. But what we want to be looking for is that we get a slight change in the degree to which the blood cell is saturated. In other words, that we're releasing the oxygen into the cell. At the same time, we also need to think about the pressure of O2 on the venous side. Remember that oxygen extraction itself is a function of what is happening on the arterial and what is happening on the venous side. So we have to have some pressure gradient between the arterial and the venous side, otherwise we don't get the flow of oxygen into and out of the cell. So you can really get an impression from just this schematic alone of how important the cardiovascular system is to this whole process. And in particular, keep an eye on this Fick equation, because we're going to keep coming back to that in terms of our understanding of exercise science. That VO2, what you measure at the mouth, is a function of the cardiac output and the AVO2 diff, and that as a whole reflects what is going on at the muscle in terms of the QO2.